So what we saw is that when there are two surfaces in contact, okay, a tangential contact force that acts between two surfaces in contact that either opposes slipping, okay, or opposes the tendency to slip. That is called friction. This morning there was no lecture on friction, Sakshi. I have not taken any lecture in the morning in this house.
Sir, it was
Sir,
covered.
Sachin sir took it.
Sorry, it was?
Sir, it
Sachin
was,
sir's lecture.
Yeah, okay. So, like, I think he will send the recording and the notes so you can cover it up from that, Sakshi, if you miss the lecture. Okay. I will continue this lecture from the point that we have discussed in the last lecture.
sir, anyways, it was a covering lecture.
It was a covering lecture for students who have either joined late or who have required it for the board level of internal exams in junior college, etc. Okay, for the integrated program. So here we'll just continue in the logical order from the previous lecture that I have taken, which was on 10th of November, I think last week. Okay. Okay, so there are two kinds of situations in which friction acts. Okay. So for example, if we are applying force on a body, but we are not able to move the body. So there's a tendency to slip, but friction is opposing that tendency to slip. So that kind of situation is happening. If this is at rest, in spite of application of some external force. So F is an external force. This creates a tendency to slip. But friction prevents slipping. So there is no slipping between the two surfaces. Then the type of friction acting, as you know, is called kinetic friction. So in this situation, the friction which will act between the horizontal surface or the horizontal plane on which the body is lying. So here, this type of friction will be called static friction. And this is applied by the surface below. And it act in such a way that it opposes the tendency to slip. So when we visualize the free body diagram, we can see that the external force that we have applied, that is giving it a tendency to slip towards the right. So if there had been no friction, then this block would have slipped along the positive x-axis or along the right direction. So that tendency to slip is prevented by applying by static friction acting on the body. And the other two forces acting, of course, are vertical forces of weight and normal reaction. But this body is at rest. So if it is at rest, so for example, in this case, if let's say the mass of the body is 10 kilograms and the external force that we are applying is, let's say, 25 newtons, and G is equal to 10 meters per second square. So what we can understand here, the conclusion from this is that F is balanced by static friction. So the amount of static friction acting is 25 newtons. Okay. And normal reaction balance is mg. So the normal reaction here is also 25 newtons. So this is what is happening in this case. Whereas, okay, so you can just make a quick note of this. Okay, now what we had also understood that static friction is less than equal to a certain limiting value. So this is called the limiting static friction.
So in this example, we have taken the external force as 25 newtons, no?
Yes, yes. Let's say the question is given, okay, that this is the data given. This is given in the question. So from that now we can find out. Now what we want to do is find the static friction and the normal reaction, the two things. So that we are done with. That is the two contact forces applied by the surface. One is normal and one is friction. So that we have done over here. Okay, so limiting static friction or maximum possible value that is given by the formula coefficient of static friction into normal reaction. Yes, very good. It's my mistake. This is 100 newtons. The weight is this 100. This is 100 newtons. Static friction should be 25 newtons. And the normal reaction will be equal to 100 newtons. That's correct. But keep in mind that the value of static friction acting could be less than the limiting value also. So here we cannot conclude from this that the coefficient of static friction is 0.25. It could be greater than that also, but definitely it is less. It cannot be less than 0.25. So that's another point we'll write down. But first we just make a brief note of this part.
So,
Yes.
so what have you written in the box in the last line?
That is the limiting value of static friction. Okay, so that depends on two things: the normal contact force and what is called the coefficient of static friction. That is mu s. So in this, n is the normal reaction between the two surfaces in contact. In this case, it is equal to weight, which is equal to 100 newtons. Okay, and the other one is the coefficient of static friction, which depends on the material of the surfaces. We discussed this about this last time. So it is a material property of the two surfaces in contact. Okay, so surfaces which have more roughness will have more larger value of coefficient of friction, like concrete against concrete. But for example, polished wood on polished wood will have lesser coefficient of static friction, or stone on polished marble will have a lesser value of coefficient of static friction. So this depends on the nature of the surfaces. So further from this, now we can also say one thing, that from the information given in this example, what we can conclude that from the given values, we can see that static friction acting, which is 25 newtons, that means this value of friction is less than equal to this. Okay, so that means 25 newtons is less than equal to coefficient of static friction into 100 newtons. That means in this case, the coefficient of static friction is definitely greater than 0.25. We can't find the exact value, but we can say that it's not less than 0.25. So this is the final conclusion about the coefficient of static friction. To check whether it is equal to 0.25 or greater, what we'll have to do is we'll have to increase the force and check when the slipping starts. Okay, we don't know right now that if we increase the force from, let's say, 25 to 27 or 30 or whatever, whether slipping will start immediately, or we have to increase the force, let's say, beyond 30 or beyond 35, or that we don't know. But suppose we increase the force very slightly and we see that, okay, the moment the force is greater than 25, the block starts sliding. Only then we can say that the coefficient of static friction is 0.25. Without that further experiment, we cannot tell over here how much the coefficient of static friction is.
Sir,
Yes.
sir, what have you written there down in the box? New S?
Yes, mu s is the coefficient of static friction.
Yes, sir, I
The
know
short
that,
form
but
of coefficient, yes.
0.25 and
Yeah,
how is
0.25.
it more than 5?
Yeah, see the equation before this, no? The value of static friction is 25, and that should be less than equal to mu s into the value of n, which is 100. So doesn't that tell you that mu s should be greater than equal to 0.25?
Oh, okay, sir. Thank you.
Right? Okay, so it's coming from substitution of the values. So we have found out कि static friction कितना act कर रहा है, 25 act कर रहा है, whereas we found out कि normal reaction कितना है, यहाँ पे it's 100. So from that we are getting this conclusion about the value of static friction. This final conclusion that we are getting is based on that, right?
So, sir, that 0.25 is not the value of nu.
No, it is not the value. It could be greater than that also, but definitely we can say it's not less than that. That's what I'm saying, no? Because I don't know that if I increase the force, whether the block will start slipping or not, whether I need to increase the force a lot more or even just increasing will make slipping. So how can I say what is the exact value of coefficient of friction? I cannot say that.
Sir, if coefficient of static friction is less than 0.25, then what will happen? The body will slip or it will not slip?
Then the moment we apply a 25 Newton force, what will happen? It will start slipping. Because imagine the free body diagram, no? Suppose the coefficient of static friction was 0.2 instead of 0.25. Then what is the maximum friction available? 20 newtons. Sir. So can a 20 Newton friction balance an external force of 25 Newton? It cannot, no?
Yes, sir.
Okay. So that's how we know कि वो 0.25 से कम नहीं हो सकता ना, because we are given in the question that the block is at rest with the application of 25 Newton force.
So,
Yes.
so static friction is like self-adjusting, depends on the
Yes.
force you're applying.
Exactly. Static friction is self-adjusting. It depends on the tendency to slip also. That is how much external force is giving it a tendency to slip. And it also depends on the other two things. The limiting value of static friction. That depends on the material of the two surfaces, so coefficient of friction. And it depends on the normal contact force between the two.
Okay, sir.
You understand? So it's a self-adjusting force. Just like normal reaction is a contact forces are generally self-adjusting, right? Okay, now next, let's see a situation where what we are observing is, now forget about the previous example. This is something which is a different situation compared to that one. So what we are observing now is that on a block of mass m, when we are applying a force, pulling it with an external force F, it has a horizontal acceleration E. So given a block of mass 5 kg pulled by a horizontal force of 30 Newton magnitude, suppose, slips at an acceleration of 2 meters per second square. Take G as 10 meters per second square. So first of all, is the surface a rough or smooth surface? And find the value of coefficient of kinetic friction in this case. So the background to this question is that we know that if there is slipping between two surfaces in contact, which are rough surfaces, okay, then kinetic friction equal to coefficient of kinetic friction into normal reaction acts tangentially such that it opposes slipping. And also additionally, for most surfaces, the value of static friction coefficient is equal to the value of kinetic friction coefficient, but in some cases, this is larger, but larger by a very small amount. It will never be the coefficient of kinetic friction is larger. If one of the two is larger, it will have to be the coefficient of static friction, which is larger of the two, and it will be larger by a very small difference. It will not be a large difference. So with this information, like, let's work out again from the free body diagram of the block. Okay, that first of all, whether there is friction acting or not. So if there is friction acting, we will say that yes, the surface is rough. If there's no friction, that's our conclusion, then we'll say that the surface is smooth. Okay. And once we've understood that, we'll also try to find out what is the coefficient of kinetic friction. So if, for example, it's a smooth surface, then your conclusion will be coefficient of kinetic friction is 0. Let's see, in this case, it is how much? Yes, that's correct. Very good. Siddharth, your answer is correct for coefficient of kinetic friction. Exactly the point, Siddharth. That's correct. So what you can conclude? So very good, Rishita, Ayan. The values are correct. Ishita, you have to check your answer once, but Rishita, your answer is correct. So what you can see here is that the acceleration of the block being how much is it? 2 meters per second square. You can see it is less than the amount of force we are applying, because I mean less than MA, or force divided by mass, because we are applying a force of 30 newtons. So you can see that the acceleration is less than F by M. So that is showing us that kinetic friction is acting. Because F by M would have been 30 by 5 or 6 meters per second square. But since the acceleration is less than that, so I'm making this free body diagram in the inertial frame and all that. Okay. So now I know that, okay, there is some kinetic friction acting. And I also know that the vertical forces are just 2 in number, normal reaction and mg. So I know from this information that F minus kinetic friction will be equal to M into A. That's my first equation. And normal reaction will balance mg. That's my second equation. So from the first equation, I can find out that I'm getting kinetic friction as F minus MA. So that is equal to 30, what is it, 10. So the kinetic friction is 20 newtons. And from the second equation, I can see that the normal reaction acting is equal to the weight, which is 50 newtons. So from this now I know, from this and this together, I know that kinetic friction is equal to mu n. So 20 Newton kinetic frictional force is coefficient of kinetic friction multiplied by 50 newtons of normal reaction. So that is telling me that the coefficient of kinetic friction is 0.4 or 2 by 5 in this case. Yes, Ethan, it's correct. Your answer now. Okay.
So,
Yes.
so like, why didn't we equate it with 10 over here? Like, that was the force at which it would have started to slip, right?
What would have started to slip the block? Why?
The object
How
would
do you
have
know it
started.
would have started? Why? How you know it would have started to slip at 10?
Because F equals to ma, then mass into acceleration, that gives us 10 over there.
So M into A is the net force, na beta? How do you know that when the force is 10 Newton, it would start to accelerate? This is the net force, no? 10 Newtons is the net force acting. That's why it has an acceleration of 2 meters per second square. So what is the net force over here? From the free body diagram, you can see that the net force is coming from equation 1. It is external force minus kinetic friction. It's not giving us the information that if it was 10 Newtons, it would start slipping. In fact, it would not start slipping, no? Because the friction available is definitely more than 10 Newtons, because kinetic friction only is 20 Newtons. Understanding? No?
Yes, sir.
Okay. So we
Sir,
have to
if the
go always.
surface would have been a smooth, if the
Ah.
surface would have been a smooth surface and the block
Yes.
is at rest, then the coefficient of static friction will also be 0.
Smooth surface में कैसे rest पे रहेगा बेटा? अच्छा, you're not
For
applying any
example, we are
external
not
force.
moving the block. We have just kept it on a table.
So it does not have any tendency to slip. No? Till you apply some external force, there's no tendency to slip. So why friction will act?
So it will be 0, no, sir?
Friction will be 0, beta. That doesn't mean coefficient of static friction will be 0. You understanding? If I don't
Okay,
apply
sir.
a force, there's nothing to oppose. No? So why friction will act on its own?
Okay, sir.
So static friction prevents the tendency to slip. No? So first of all, there has to be some tendency to slip. Only then it will act. No? On its own, it will not randomly act. No? I have to apply some external force giving the body a tendency to slip. Then if there is static friction between the two surfaces, it will try to oppose that tendency. And if there is no static friction, then it will move according to the equation F is equal to ma. Then whatever force I'm applying, that will become mass into acceleration. Got it? Huh?
Okay, sir. Thank you, sir.
Okay, so now let us look at the next level of question in this to understand this better. Okay. So what we are doing is, so we'll take the same situation because we become familiar with it now. Then we'll gradually start looking at more complicated situations. But we'll start playing around with different values now. Okay. So we've got a block at rest initially. And this surface has two values given to us. Coefficient of static friction is given to us as 0.27 and coefficient of kinetic friction is given to us as 0.25. So this is that situation where we have two different coefficients. Okay, it doesn't always happen this way. In most questions you will see that the question gives you a common value of mu instead of mu s and mu k. So that means they are both having the same value, which is the common value. But here in this question, it's given to us that they have different values. Okay, and also given that the mass of the block is 10 kilograms. We will take G also as 10 meters per second square. So a block initially at rest on a rough horizontal surface Now, in the first part of the question, if a horizontal external force of 20 newtons acts, find the block's acceleration, if any, and the friction acting on it. Second part of the question, if again a horizontal force of magnitude, this time we'll make it 26 newtons, acts on the block, again find the acceleration and friction. And next part, we'll do this question in three parts initially. If a horizontal external force of 30 newtons magnitude acts on it, then again find the acceleration and find the friction. And when I say find the friction, you have to also state what type of friction it is. Is static or kinetic friction? Exactly, Rishita. What happens is that most surfaces have a tendency that if there is no slipping occurring, then there is better grip. Okay, so the amount of friction available, the limiting friction available is more than the kinetic friction. Because once the slipping starts, because the surfaces are not able to interlock and grip each other that well, so the amount of friction reduces slightly from the limiting static friction. So this actually happens in reality for all surfaces. But the difference is that for most surfaces, the difference is so small now that you can't really measure it. So we take the value as same. Like here also, you can see the difference is, of 0.02. So in terms of a percentage difference, it's a very small difference. If you take coefficient of kinetic friction 0.25 and compare, so a difference of 0.02 is like a difference of 4%. Difference of 8%. In most cases, it will be a very small difference. Instead of 8%, it will be 0.8% or 0.2% or something. So it's absolutely negligible. Even if we write the coefficient up to second place of decimal, it will come out to be the same. So we neglect that difference. But in reality, always two surfaces at rest are able to grip better. So the amount of static friction's limiting value will always be greater than the kinetic friction. I hope this point is clear.
Yes, sir. Thank you.
Yeah. Okay, now make the free body diagram. Always systematically, you have to start with the free body diagram in any problem related to application of force and dynamics and Newton's laws concept. And from that, you'll be able to systematically work out each of the three parts. Try to get the answer correct. Okay, I started getting some answers. Khushi, your conclusion is correct. Okay, for the first part, but the value of friction that you're writing is wrong. Okay, make sure that the net force acting on the body is according to the acceleration. Rishita, correct? Very good. Ishita and Rishita, both of you got the answers correct. Siddharth, your answer is also correct. Very good. Yes, very good, Rishita. Your second answer is also correct. Okay, so now that some people have reached the second part, I'm going to put up the answers first. I'll discuss the solution later. Yes, very good, Rishita. All three answers are correct. Also, tell me the acceleration in the third case. Huh? So this one,
So,
the acceleration will be 0 and static friction of 20 Newton meters. This one also the acceleration will be 0, but static friction of 26 Newton meters. In this case, the acceleration will become non-zero. Okay. Yes, Ishita, correct for the second one also. Yes, very good, Krish. Your answer is correct. So there will be an acceleration of 0.5 meters per second square because there will be kinetic friction acting and that will be only 25 newtons. That won't be 26 or 27 newtons. Yes, correct, Ishita. Very good. So now let me explain both the cases possible here. Okay. So depending on how much force we apply, because the block is initially at rest, whether we are able to overcome the limiting static friction or not, that is what will tell us first of all that whether there is acceleration or not. So we can see from this that, and everything I'm working out in the inertial ground frame. Later we'll see problems where we might have to incorporate non-inertial frame concept here also, problems involving friction. So anyway, normal reaction is equal to weight. So the normal reaction is equal to 100 newtons. Correct. Or is it 50 newtons? 100 newtons, yes. So from this, first of all, we can understand that the limiting static friction, which is coefficient of static friction into normal reaction, is 27 newtons. Whereas the kinetic friction, which is coefficient of kinetic friction into normal reaction, is 25 newtons. So from this, we understand now that when we apply some external force, what type of friction acts and whether or not there is acceleration, that all depends on the value of the external force, because initially the block is at rest. So from that we understand that if capital F is less than equal to 27 newtons, then the acceleration will be 0, okay, and static friction balancing the external force will happen. The static friction need not be, so when for example the external force is only 20 newtons, there won't be static friction of 27 newtons acting on it, because that would be unnecessary. No? It could cause the block to accelerate in the backward direction. We don't want that to happen. The block should be at rest. So how much force is required to keep the block at rest? Only 20 newtons. So only 20 newtons will act. Whereas the moment my external force exceeds is greater than, let's say, 27 newtons, my acceleration will become non-zero. It will start slipping, and kinetic friction of mu k into n, or 25 newtons, will act. So we'll have the equation for this, that F minus kinetic friction is equal to ma. Whereas for this, we'll have the equation that static friction is equal to external force. So so the final conclusion in my FBD will depend on which value it is. So for example, in the first case, we have taken F as 20 newtons. So this will be that case where static friction acts. Static friction prevents slipping, or prevents the tendency to slip. So my external force is just balanced by an equal and opposite static friction, which keeps the block at rest. Same in the second case also. Same type of FBD. But the static friction will now be 26 newtons. The acceleration will be. But in the third case, you can see F is 30 newtons. So now there is slipping. Slipping occurs. So we can see in our FBD, we have to specify the type of friction acting as kinetic friction. And we have to show that the block has a non-zero acceleration. So we'll have the equation that F minus kinetic friction is equal to ma, where kinetic friction is mu k into n, which is 25 newtons. So 30 minus 25 will become 10e. So this type of kinetic friction acts, and the acceleration is equal to 0.5 meters per second. Okay, so this is the third part of the question. Make a note of these free body diagrams. Now we'll do another part of the question, which is very interesting. Okay, so now the block being initially at rest, at t equal to 0, a constant horizontal force of F equal to, we'll again take this as 30 newtons. It acts from t equal to 0 to t equal to 10 seconds. Okay. After t equal to 10 seconds, this external force stops acting. So find the acceleration of the block from t equal to 0 to t equal to 10 seconds, which you've already done, and from t equal to 10 seconds onwards. And now we'll make some kinematics in this, and we'll show that find the velocity as a function of time t, and plot the velocity versus time graph. Okay, so if you finish with the first three parts, start working on this part. And this part's the initial part of the motion is something that you already solved in the third free body diagram above. What is happening from 0 to 10 seconds, you already know. But using that FBD and the acceleration, you have to also work out the kinematics of the block now. That is, the velocity is a function of time. And also you have to be careful and understand what's happening after 10 seconds when we stop applying the external force. So this will also explain something important about kinetic friction to us.
Sir, can you scroll up?
Yeah, I can scroll up, but the
First
solution
part
of
is
the
the starting of the solution. Yes. The starting of the solution.
okay.
So now you can scroll down.
Yeah.
A little bit of the second part.
Okay. Okay. Yeah, Rishida, you have given the answer for 1B part. That's correct. Very good. A part, so you know the answer for the acceleration will be just 0.5, which you already calculated.
So profit.
Oh, Rishida, you have to, I think, check the solution. Yeah, it's correct. Just check your calculation for the B part, but I think there's a error in the decimal place, Rishida.
Okay, sir.
So you are correct in saying there will be a
Yes, sir.
deceleration.
Sorry,
Yeah. You divide by 100 by mistake, no? Instead of by 10.
Yes, sir.
Okay, no problem. Okay. So now see, we have to understand what is happening from 0 to 10 seconds. We've already seen that before, but let's also understand the kinematics of it. So we start applying this force of magnitude 30 newtons at t equal to 0 when the initial velocity was 0. So from then only kinetic friction starts acting. The moment we apply this force, now I'm not showing the vertical forces. You already know that. So kinetic friction of 25 Newton starts acting. So it develops a uniform acceleration of 0.5 meters per second square. So from here, the block starts moving. And let's say at t equal to 10 seconds, it reaches somewhere here. So t equal to 10 seconds. Now what its velocity would have become? Velocity would be a into t. So it would be 5 meters per second. Okay. Because from t equal to 0 to 10 seconds, the acceleration of the block will be F minus kinetic friction upon m, which we already worked out is 0.5 meters per second square. So for this time, the initial velocity is 0, the acceleration is 0.5. So the velocity at any time will be 0.5 t for any time between 0 to 10 seconds. So anytime in between this also, you can see that we continue to have that acceleration. 0.5. Because both the forces are continuously acting. Now what happens is that at this time t, we withdraw the external force. So now onwards, it starts decelerating. So let's say it decelerates at A prime. It's not that friction will stop acting because it's continuing to slip now. So for example, even at some time greater than 10 seconds now, if it has some velocity, then friction has to act because it's slipping, and accordingly it has to decelerate. This process will only stop after some time when the object stops altogether. Its velocity becomes 0, then friction stops acting. So that will also happen at some time and the block will remain at rest. So from t equal to 10 seconds onwards, the block has a deceleration A prime equal to kinetic friction divided by mass. Because you can see in the FBT, there's only one force acting horizontally. So kinetic friction was 25 newtons divided by the mass. So it has a deceleration of 2.5 meters per second square. So you can see that it will stop at what time? It will stop at, so at t equal to 10 seconds, its velocity was 10 meters per second square. Sorry, 5 meters per second. So it will move for another how much time? Another 2 seconds. So at t equal to, let's say, 10 plus some additional time delta t, the velocity would have become 5 minus a prime into delta t. So it will become 5 minus 2.5 delta t. So v becomes 0 at delta t equal to 2 seconds. Okay, so that means t equal to 12 seconds. And from 12 seconds onwards, the block remains at rest. So this shows us the important lesson that kinetic friction, it does not depend on how much external force we are applying or what direction we are applying the external force. It just depends on the direction of slipping. So from 10 to 12 seconds here, you can see we are not applying any external force, but still slipping is taking place because the block already had some momentum. So kinetic friction continues to act in such a way that it opposes slipping, and it acts till the object comes to rest. Now, once it comes to rest, now no friction will act because it doesn't have any tendency to slip anymore because we stopped applying external force. So our velocity versus time graph, the initial part from 0 to 10 seconds will be like a uniformly accelerated motion. And then from 10 to 12 seconds, which is comparatively smaller amount of time, it will act like a uniformly decelerated motion. So the first part of the motion is it's having an acceleration of A equal to plus 0.5 meters per second square. But the second part is having a deceleration and a very sharp deceleration. So it takes only 2 seconds to come to rest, whereas it had been accelerated for a lot longer. It had been accelerated for 10 seconds. Because now it has an acceleration, which you can write as minus of A prime because it's a deceleration. So it's minus 2.5 meters per second square. And in between these two, just as its motion is switching from accelerated motion to decelerated motion, it reaches the maximum velocity it would have had at any point of time, which is 5 meters per second. So this is what is happening from t equal to 10 seconds onwards up till 12 seconds. And this is what is happening initially from 0 to 10 seconds.
Sir, does friction depend on the shape of the object?
Yeah, I mean the coefficient of kinetic friction in that sense will depend on the shape in the sense that how rough the surface is. Okay. But if you are saying like this, that if you have, let's say, a cuboidal block and you change the surface from a larger surface to a smaller surface, whether the kinetic or static friction will change, it will not, because the normal reaction will remain the same and the coefficient of friction will remain the same as long as all the surfaces have the same material.
So sir, if I make a rubber with a base of with a circle with a base touching is equals to, let's say, 2 centimeter, and I have a square of rubber of 2 centimeter, both will have the same friction?
Probably not, because your circular object will have a different weight compared to the square object. So normal reaction will be different. But if you made them such that their shapes are different but their weights are same and they're made of the same material, then yes, the normal reaction being same, the friction will be the same.
So,
Okay,
but
sir.
in a so,
Yes.
but in a circular, there would be like rolling. It would be rolling, right? So there
You
might
can
be a
make it
difference.
slide also. You can make it slide also by pushing it in a different way, in which kinetic friction will, in which case kinetic friction will act.
Okay, sir.
If it's a cylindrical object or a spherical object, you're correct that generally when we apply force, it will have a tendency to roll. But if we apply too much force or if we grab hold of it and make it slide in that way, such that it's not rolling, then the friction acting will be kinetic friction.
Got it, sir. And so I had a doubt in the part like how you found out the time of 2 6.
Time for it to 12 seconds, no? When it stopped.
So like
That,
you just subtracted 2.5 from 5 every time
no,
every
not
for
2.5 from 5 beta. 2.5 is the deceleration. So see this equation that I've written over here after this 10 seconds part. V at 10 seconds is how much? 5 meters per second. So now if I see some time after 10 seconds, 10 plus delta t. So this deceleration of 2 meters per second square is acted for how much time? Delta t time. No? So the velocity will be the initial velocity. The initial velocity is now the velocity at 10 seconds. Okay. Minus a prime into delta t. That is how much time I've gone beyond 10 seconds. Understood? No?
Yes, sir.
So for example, you can see at 11 seconds time, delta t would have been 1 second. So what the velocity would have become? 5 minus 2.5. It would have become 7.5. So like that, at how much time the velocity is becoming 0, that's when 5 minus 2.5 delta t is becoming 0. So that delta t is 2 seconds.
Yes, sir.
Can you scroll up in the fourth question?
Yeah.
So what is written after a?
After
After at t is equal to 0, comma a, the first line.
At t equal to 0, constant horizontal force. That's short form for constant.
Yes, sir. Sir,
Okay, so this is completed, I hope.
sir, wait.
Okay.
So what is written after the t is equal to 10 seconds onwards?
The block remains at rest, which you can see in the velocity time graph also. The block now remains at rest.
No,
Because
this
friction.
written onwards, the block has a what is written after the block has a
Deceleration. This one, this is deceleration. Yeah, I will send you the notes now. You can complete the notes later.
the
You
last
understand?
part is only left. Last part.
Okay, be fast because it delays the whole class. Okay. That's why I send you the notes so that you can complete your note writing later. Just understand the method of solving the question carefully here.
Okay, sir.
You don't have to write each and every sentence in detail. It's not required. You have to understand the solving method and you can later refer to the notes for all that.
Okay, sir.
All right, now let's come to our next example. A block on a rough inclined plane. So now I'm giving a single value of mu. That means you're assuming coefficient of kinetic friction is equal to coefficient of static friction. So a block of mass m is gently placed on a surface as shown and released from rest. The mass of the block is 5 kilograms. G is equal to 10 meters per second square. Now in the first case, if
Sir,
the
theta?
coefficient of friction, yeah, I'll tell you the values. So if the coefficient of friction is 0.8 and theta is equal to 37 degrees, then find acceleration. If any, and the magnitude of friction. In the second case, if the coefficient of friction is 0.6 and the angle of inclination is again 37 degrees, again find in this case coefficient of static friction is equal to coefficient of kinetic friction equal to mu. So take down the values and make the FBD of the block. Make the free body diagram, first step. And from that, find the limiting friction condition. From the limiting friction condition, you will understand whether or not the object is slipping. And if it is slipping, how much acceleration it has. Because which is the force which is giving it a tendency to slip? It will be the component of weight which is parallel to the inclined plane. Whereas which is the force which is giving it the contact force with the ground, which is creating the normal contact force with the inclined plane. It is the component of the weight which is perpendicular to the inclined plane. Okay, so you have to break the weight into the components. You have to resolve weight into the two components to understand what is the component parallel to the inclined plane, which is giving it a tendency to slip, and what is the component perpendicular to the inclined plane, which is creating the normal contact force.
Sir, I've said the answer.
Okay, so let's understand the method of solving this type of question. Then we'll come to the answers and all that. So what's happening is that the moment we've kept an object on the inclined plane, you know that the component of its weight, we have seen this from Newton's laws before. If this angle is theta, then the angle that the vertical makes with respect to the inclined plane, that is also theta. So a system of axes, this angle is theta, this angle is theta. So when I take the components of mg, we have the component this is mg cos theta and this is mg sin theta. Normal reaction acts like this, and here friction will act like this. So normal reaction is mg cos theta. So maximum limiting friction available will be equal to mu n. So it will be mu mg cos theta. So therefore we will see that if mg sin theta is less than equal to mu n, then the acceleration will be 0 and static friction equal to mg sin theta will act. Whereas if mg sin theta is greater than mu n, that means the acceleration will be non-zero and kinetic friction equal to mu mg cos theta will act. So this is, so in first case, our theta is equal to 37 degrees and coefficient of friction is 0.8. Okay. And mass of the block is 5 kg. So we can see that the normal reaction, which is mg cos theta, will become 40 newtons. So the maximum limiting friction will be 32 newtons. Okay. Whereas mg sin theta is only 30 newtons. So you can see that mg sin theta is less than mu n. So this will be the case where the acceleration of the block will be 0 and mg sin theta is just balanced by a static friction. So 30 newtons of static friction acts. Even though the maximum friction available is up to 32 newtons, but how much friction is required to prevent slipping? Only that much will act. The second case will be different. Second case, you will see, just putting up the values for the second case. We are taking theta is again 37 degrees, but this time we are taking coefficient of friction as 0.6. So see what happens in this case. So this is the slipping condition. This is the no slipping condition.
Sir, I sent you the answers. Are they correct?
Yes, very good, Ethan and Kushi. Answer is correct for the second part. Ethan, just a slight adjustment in the first part. Hope you understood. So in this part, you can see theta is equal to 37 degrees, but coefficient of friction is 0.8. Mass is 5 kg. So once again, we can see normal reaction is 40 newtons. But this time the limiting static friction, sorry, this is 0.6, not 0.8. So that is only 24 newtons. Whereas mg sine theta, that is 30 newtons. So this is the case where mg sine theta exceeds mu. So there is slipping. Okay, so once there is slipping, in our free body diagram, we have to find out the acceleration by finding the net force along the inclined plane, which is mg sine theta minus the kinetic friction which will act. So this kinetic friction will be mu n. So mg sine theta minus kinetic friction is equal to mass into acceleration. So mg sine theta minus mu n is equal to ma. So further, mg sine theta minus mu mg cos theta is equal to ma. So now we can see that this was 30 newtons, but this is 24 newtons. An acceleration of 1.2 meters per second square. So now we can kind of make a theorem out of this. We can see that for a block on an inclined plane, mass m, normal reaction is mg cos theta, and limiting static friction is mu s into n. So condition for no slipping is that mg sine theta should be less than equal to mu s into n. So when you substitute that over here, you can see you get a relation that coefficient of static friction should be greater than equal to tan theta. This is the case when no slipping occurs. And therefore the opposite of that, then the block will slip. With acceleration equal to,
Sir, when mu s is equals to tan theta, then theta is equals to the repose angle, no?
yes, so that particular angle is given a special name. It is called the angle of repose. So for a given surface of coefficient of friction mu s, if tan theta is equal to mu s or theta is equal to tan inverse mu s, then this theta is called the angle of repose. So this is the limiting angle for the given surface. For example, if coefficient of static friction is, let's say, 1 by root 3, then theta is equal to tan inverse is 30 degrees. So 30 degrees is the angle of repose, which means that for theta greater than 30 degrees, there will be slipping, and theta less than equal to 30 degrees, there will be no slipping. So that is the significance of the angle of repose. Okay, so hope this concept of angle of repose is clear from this definition. And now the below example, if the coefficient of static friction for a certain surface is equal to 1 by root 3, so that means for this particular surface, the angle of repose will become 30 degrees. So if I increase the angle of inclination beyond the repose angle, which is 30 degrees, then a block will tend to slide when placed on it. Whereas if I keep it less than equal to 30 degrees, that is the meaning of the angle of repose. It's like that limiting value of theta, that if I incline it more than that, it will create slipping. If it is less than equal to, then the block is safe from slipping. There is enough friction to prevent slipping. Okay, so let's now look at another problem on an inclined surface to make these concepts further clear.
Can you scroll a bit up for 5 seconds?
Yes, just give me a moment. So this time we have an incline of 30 degrees. We have a block of mass m. Now this has a coefficient of friction of 1 by 2 root 3. Okay. And the mass of the block is 10 kgs. We'll take G also as 10 meters per second square. Now what we do is we start applying a force F like this, parallel to the inclined plane. Yeah, I'll scroll up, don't worry. We just finished writing the question. So a force parallel to the surface is applied on the block. Find the minimum magnitude of F such that the block remains at rest and the block starts to slide up the incline. So two different situations. Okay, so we'll come back to the question. Just when finish writing down this part, if you like.
So done.
Okay, so let's come back to the question. So the coefficient of kinetic friction is, the coefficient of friction is given to us in terms of root 3. Theta is the angle of repose. Even in that above question, coefficient of friction was 1 by root 3. So angle of repose, theta r, was tan inverse of 1 by root 3. So that's how we got it to be 30 degrees. That was the example. Okay. Okay, Siddharth, the answer that you've given, it is not the minimum force. If you apply that value which you've given, yes, the block will remain at rest, but also we will not be utilizing friction to whatever maximum we can. And there is more friction available to us. So we can actually get away by applying lesser than the amount that you have mentioned in that message. Okay. Probably you have taken zero friction in your solution, in your FBD. Now just think, if we were to apply a force of less than 15 newtons, okay, can the block still remain at rest? Yes, because there is static friction available to us. So the question is, up to what value I can go? Okay, so I hope you're understanding the point.
सर आंसर आ गया.
What the answer? Wait. Yes, Rishita, your answer is correct. Siddharth, your answer is not correct. The first one. Yeah, Krish, yours is correct now. No, now Rishita, for the B partner, what you have to understand is that if you make the object slide upwards, now friction is opposing its motion. So visualize the free body diagram, and if it's sliding upwards, what type of friction is acting? Kinetic friction. And what is the direction of kinetic friction? That also you have to understand.
Yes, sir.
Yes, very good, Krish. That's correct. For the second part also. Okay, so this is what makes this type of question very interesting. That first of all, you analyze the components of weight. Okay. So understand that the mg sine theta that we are working with, that is how much over here? That is 50 newtons. Okay. And mg cos theta that we are working with, that is 50 root 3. And mg sine theta is 50. So naturally the normal reaction is equal to 50 root 3. So mu n is 1 by 2 root 3 into 50 root 3. So that's 25 newtons. So we keep this in mind that the maximum friction available to us has a magnitude of 25 newtons. Keep that in mind. Okay. So now when we apply a force like this, when we are pushing this object with an external force like this, so there are several possibilities. So for example, if F is exactly 50 newtons, then what will happen is that the acceleration of the block will be 0 and there won't be any friction acting because there's no tendency to slip. Okay. If F is less than 50 newtons, okay, then it can happen that the acceleration is 0, but there should be enough friction to prevent the slipping then. Okay, so if we are applying some force of less than 50 newtons, we can still keep the object at rest because there is some friction available to us. And acceleration of the block is 0. Then F plus static friction together are balancing mg sin theta. Okay. So F plus static friction is equal to 50. So static friction that we require is, okay, now we know that static friction is less than equal to mu n. So it's less than equal to 25. Okay. So now this statement, we substitute this here. So we see that 50 minus F should be less than equal to 25. So that means F should be greater than equal to 25 newtons. So we can see that the minimum value of force that we require is 25 newtons for acceleration to be 0. For F less than 25 newtons, what will happen is that the block will slide down the inclined plane. Because in this case, what will happen then is that in spite of this force, there will be a kinetic friction of this much acting. The block will accelerate. Have an acceleration like this. But in this case, or this case, the acceleration will be 0. So this is this. Now we'll also see the case where what happens if the force is more than 50 newtons, then there's a tendency to slip up. Okay. And again, there is a possibility that we are not able to make it slip in spite of applying a force of 50 newtons because friction is able to prevent slipping. Or there's a tendency that friction is not able to prevent slipping and ultimately there is acceleration in the upward direction. But the moment the capital F is more than 50 newtons, that is more than mg sin theta, the direction of friction will switch.
Sir, done.
Okay, I'm just checking out the answers. Yeah, because here F is less than 50 newtons. No? So whether or not it is static friction or kinetic friction, the tendency to slip or the actual slipping is in the same direction, down the inclined plane. So whether it's kinetic friction acting in this diagram, Ethan, or it's static friction in this diagram, okay, which is for this case, the friction is acting opposite mg sin theta because the tendency is to slip down the inclined plane. Now it is only when F is greater than 50 newtons. Now there is a tendency to slip up the inclined plane. So the direction of friction changes. Now F is dominating over mg sin theta. No? So friction has to help mg sin theta to prevent slipping, or at least to try and prevent slipping. So now the moment our force F is greater than 50 newtons, there's a tendency to slip up the inclined plane. So friction starts acting down the inclined plane like this. So if F minus mg sin theta, that is the net force up the inclined plane, is less than equal to mu n, then there is no slipping. So F minus 50 is less than equal to 25, or F is less than equal to 75 newtons. There is no slipping. But if F becomes greater than 75 newtons, then there is slipping up the incline. So if this is static friction, the acceleration will be 0. So that is this case. Whereas this case, the force we are applying becomes more than 75 newtons. Then we will not be able to prevent the slipping. So the friction acting will be kinetic friction equal to mu n. Okay. And there will be acceleration like this. So the minimum force we need, like a limiting value, for it to slip up the inclined plane is a force slightly greater than 75 newtons. Even exactly at 75 newtons, it will not slip. So Krish, your answer is correct. The force should be greater than 75 newtons. Okay, so Rishita Beta, I hope you understood this part also.
Yes, sir. Now I understood it.
Now you understood now how the direction of friction switches, no, once your F becomes more than 50 newtons. So now you have to overcome mg sin theta plus friction for it to slip up. So that's how it becomes 75, right?
Yes,
Okay,
sir.
so
We added it, right? So
correct. Okay, so this is quite an advanced level problem in friction. So don't worry if you initially were not able to solve it yourself. Okay, this will be the more tricky type of questions in NEET level, or more like a JEE Advanced level question, even you can say. Okay. But anyway, with more practice and couple of more lectures, we will learn all the various tricks. Today, angle of repose was something important, and this kind of analysis between static and kinetic friction. So we'll conclude today's session here, people. We are out of time now. So up to next time, you continue working on problems from H.C. Verma from the friction chapter. Now you can do up to about question 20 in the friction chapter, and for students of NEET, you do problems from exercise 1 and from the in chapter exercise of your module from friction. That's it for today's session, people. Wish you all the best. Have a nice day.
Thank you, sir. Bye bye, sir.
Thank you, sir. Bye, sir.
thank you, sir.
Thank you, sir. Bye.